Okay, on 1.8, what we're doing is looking at the combination of functions in different ways. The first part we're going to look at in terms of addition, subtraction, multiplication, and division. And then after that, we will move into composite functions. So to help us understand the combination of functions by basic addition, subtraction, multiplication, division, I offer you the situation of the years from 1990 to 2004 and the number of SUVs sold in each year and the number of cars sold in each year. So the first function that we're going to look at is C of x, which represents the number of cars sold in the year x. So x would represent the input of years, and then C of x represents the output, how many cars sold in millions. And the same for S of x. S of x represents the number of SUVs sold, and x represents the years it was sold. So if we want to find C of 96, what we're going to do is go to the year 1996, and then C, which is right there, and it's right above 8 million, probably about 8.5, but just for nice round numbers, I'm going to put it as 8. So what this function tells us is that in the year 1996, there were approximately 8 million cars sold. And then S of 96 in the year S of 96 means in the year 96 how many cars were sold, and that would be 2 million. So now I pose the question, if cars and SUVs, let's just imagine the simplistic world that cars and SUVs were the only vehicles on the road, how many total vehicles were sold in the year 1996? And what we do is we would add these 8 plus 2, which would be 10 million. The way we would write that would be C of 96 plus S of 96, or 8 plus 2, which equals 10 million. Now I pose the question, how many more SUVs were sold, and how many more cars, were sold than SUVs in the year 1996? And that would be 8 minus 2, which would be 6. So that would be in our function notation C of 96 minus S of 96, and that would be 8 minus 2, which equals 6. What is the ratio of the two of them? And that would be C of 96 divided by S of 96, and that would be 8 divided by 2, which would be 4, or 8 divided by 2. So these are the combination of functions, and now these are totally new functions that we've created. And we're going to get into that notation in a second. Now we've created a new function which would represent the total vehicles sold in the year 1996, or in general, the difference of them, and then the ratio, and then we could imagine the product of two functions. It doesn't really make sense why we'd multiply the number of cars times the SUVs, but we could easily think of if we have one function that represents the length of a rectangle, and then another function represents the width, the multiplication of them would be a new function that represents the area. So coming over here, let f and g be two functions. The sum, difference, product, and quotient are all new functions, where if I add f of x plus g of x, we have a new function which is called f plus g of x. The subtraction of them creates a new function. Instead of it being called f or g, it's called f minus g. And to find this new function of the product would be fg of x, and then the quotient would be f over g. So this notation is a little more complicated because it has an f plus g, f minus g, and so on. But remember, what's inside parentheses here in front of the x just represents this new function, which was created by the addition of these, this one by the subtraction, and so on. So in terms of calculating, if we have these two functions, f of x and g of x, and we want to find this new function, f plus g of x, we simply are going to add the two functions together. So f of x, which is 2x plus 1, plus g of x, which is, 6x squared minus x minus 2. And then we go ahead and combine like terms. So f plus g of x, this new function, would be calculated by, in standard form, 6x squared, cross it off. 2x minus x would give us 1x, and then 1 minus 2 would give us negative 1. Next one, f minus g, which is right here, would be created by going 2x plus 1 minus 6x squared minus x minus 2. I'm just going to write an equal sign in the interest of time. So distribute the negative, combine like terms. So we get negative 6x squared plus x plus 2, and then that plus 2x plus 1. And then we combine like terms. We'd go below it, but I'm running out of room. So we have negative 6x squared. Cross that off. 3x. I'm just combining like terms here. 2x plus 1x. Cross those off. And then 2 plus 1 would be 3. So this is the new function that would represent the difference. And then you go through multiplication and division of those, and you can look at the notes for the work on those. If we come down to a real life example, we would do the same thing. We would just add like terms between the v and the t and interpret what v plus t d of t means. Again, you can look at the notes for that. V plus t would be the total number of devices sold, and then in v plus d of 10 would be how many devices sold in the year 10, which if 1997 was the year 7, as it says right here, 10 would be the year 2000. So v plus d would be a function that would be calculating the number of total devices, playback devices, VCRs plus DVDs, sold in the year 2000. Of course, we've technologically advanced past VCRs as well as, for the most part, DVDs. Okay, now moving on. What happens when we have a graph and we need to calculate this new function and efficiency-wise, we don't even have to graph f minus g. We can just use our graph here because remember, f minus g is the same as f of 1, sorry, ran out of room, minus g of 1. And it's important, again, to understand what this notation means. F of 1 means what's the output of the function f at the input of 1. So if I go to the input of 1, my output is 2. So I am going to replace f of 1 with 2, and then I'm going to subtract it from the same. G of 1 is 3, and I'm inserting 3 for g of 1. So now f minus g of 1 would be 2 minus 3, which is negative 1. We're going to do the same for fg of 4 would be the same as f of 4 times g of 4. F of 4 is saying what is the output of f at the input of 4, and if we do that, we get 4 out. So we have 4 times, and then we do the same for g of 4. G of 4 output is 0, so 4 times 0 obviously gives us 0. Next, we have this circle notation, which represents followed by, or the composite of the functions, which we'll come back to after we talk about that here. So the other way of combining functions is what's called a composite function. To help us understand this, let's talk about this example that I give you in terms of buying a computer. So if we read through all of this, it says there's 2 sales that are given at a computer store. The first one is a sale where it's just $300 less than the regular price, and that would be f of x equals x minus 300. So if x is our regular price and we subtract 300 from it, that would then give us our new sale price. The other discount would be 85% of the regular price, which is a 15% discount, and that would be represented by g of x. So let's come over to here. At the store, you bargain with the salesperson. Eventually, she makes you an offer you can't refuse. The salesperson will be putting a 85% regular price discount, then followed by a $300 reduction. So they've given you both discounts. That would look like this, where the first thing that happens to x is the g function, which is 0.85x, and the second thing is followed by minus 300. So what would that look like? Well, if we come back to these 2 functions, that is taking g of x and inserting it to the input of f of x. If we did that, we would write it like this: f of x minus 300. And if I insert the function g of x, because remember, this right here is a value in itself. In this case, in general, it's 0.85x. If I insert that into x, I get that function that I'm looking for. This is called a composite function, where we insert one function into the input of another function. And the notation that mathematicians have created for this is this fog notation, where this is a new function which is read as f followed by g of x. And the way that we determine f followed by g of x is that this second function, whatever this is named, is inserted into f. So the two ways we can read it is f of g of x, or f composed with g of x, or f followed by g of x. In terms of the domain of this function, x is in the domain of g. It has to be in the domain of g. So if some value doesn't insert into g of x, then it can't be a input of f followed by g of x. And furthermore, g of x is in the domain of f. So whatever the output is for g of x has to be in the domain for f. And we'll talk more about how to determine domains of f followed by or f of g of x. We won't be going much into detail with that though. Okay, so let's do some basic calculations here. F followed by g of x, let's go ahead and do that first. So f followed by g of x means we take the first function f right here, and written, we are going to write that out, and remember, we're inserting into that, and that's where that open parentheses acts as a nice crutch for us. And now, since we're doing f followed by g of x, we are taking this and inserting into x, so this goes in right here. So x squared minus 3, and then in the interest of time, I'm not going to do it. It's in the completed notes. You are going to FOIL this out, distribute it out, combine like terms. The other way around would be g followed by f, and g followed by f means now we're writing out the f function, which is x squared minus 3, because that's first in this notation. But f is going to happen first to x, so x squared plus 1 acts on x, and then followed by g by taking this and inserting it into here. So we have x squared plus 1, and then again we distribute combine like terms for that. Next we have f followed by f, and that means we're taking f and inserting it into itself. And why would we do that? We'll see what that looks like later. Or why in general would we insert a function into a function. So again, our first function in this notation is f of x, so x squared plus 1, and then we are inserting to it f, which is the same function. So it goes into itself, and then again, we go ahead and distribute accordingly and combine like terms. Okay, now let's come back to this example right here, g followed by f of 3 and f followed by g of 1, when we have a graph given and not an algebraic function. So g of f, or g followed by f of 3, means g of f of 3, where now when we have this situation of a graph, it really helps to think of this as g of f of 3. And also the same idea of f of 3 being inserted into g. So what does this mean? That means we're going to take 3, insert it into the function of f, and that's going to give us an output. That's a number. Whatever that output is gets inserted into g, and then we find the output of that function for g. So let's take 3 first and insert it into f. F is over here. I look for 3. I find the output. F of 3 equals 2. So I'm going to insert a 2 for f of 3. And now that 2 is the input of g. So we come over to g of the input of 2 and find its output, which equals 2. F followed by g of 1. That means f of g of 1, which means we are going to insert 1 into g. So we take 1, insert in g, and we get out 3. And so that will now look like this, f of 3, because g of 3, or excuse me, g of 1 is now 3, and now 3 is the input of f. So we go over to the f graph. Oops, sorry, it didn't get connected. There we go. So now we have f of 3, and so we go to the input of 3 for f, and the output is 2. So we come over to here, f of 3 equals 2. Lastly, we're going to look at decompositive functions where we're going backwards, where instead of trying to compose the function, we're going to decompose it. So if you look at this notation right here, it says we want to find f followed by g of x for it to equal this function that's given h of x. So again, that's going to be the same as f of g of x equals h of x. So what we're saying is, how was this function created? What function was inserted into the other? The one exception there is that g of x cannot equal x, because that really doesn't decompose the function at all. That would be the exact, h of x would then equal f of x. So we want something different than that. So I offer you two options here. For the b, for a, we really only have one option. And what I look is I go, okay, well, there's a root function there. I'll go ahead and zoom in. There's a root function there. So that looks like an outside function. That's our f of x. Well, what got inserted into the root function? And that would be 9 minus x. So what we do is come down here and we go f of x is that outside function, which would be root x, and then g of x is inserted into that, and g of x, what's underneath the radical, would be 9 minus x. For b, we have multiple options because of the way that the function's set up. So f of x, one thing I could say is, oh, I have that parentheses there, the 5x plus 2 squared. So I'm going to make this, I'm just going to reinsert an x for that 5x plus 2. And then g of x would be equal to what got inserted into that, which would be 5x plus 2. The other way we could go about it would be 4 over x and the whole denominator, and then, so this would be one answer, and then this would be g of x, which was what was inserted in for x. It's what we have in the denominator, which is 5x plus 2 squared.